Hi, I'm Keenan Casey for tutsplus.com. In this lesson, we're going to be looking at hierarchical clustering. In hierarchical clustering, we basically arrange all of our training instances in a hierarchy. That means we'll be creating a binary tree of each of the training instances and grouping them into clusters in that way. The nice thing about this is that it has a very clear visualization, as we see here on the right. The hierarchy is created using a distance measurement between instances and choosing the closest ones and grouping them together into clusters. We'll conclude with the discussion about computing distance between clusters and talk about whether or not there's any significance to this type of clustering. These are the terms that we'll be using in this lesson. First, our input vector, x, will be of n dimensions. Our features, there'll be n total features, which is the number of columns in the data set. We'll have m training instances, and the distance function we can abbreviate in this way, the distance between two vectors x and v. This computes the similarity or distance between the two instances. There are two approaches to doing hierarchical clustering. The first is agglomerative, and in this approach, we take a bottom-up view. Each training instance starts its own cluster, and pairs of clusters are merged together as we move up the hierarchy. The other is the opposite approach, divisive, and that means that we start at the top and move down. In this case, all the training data is in one cluster, and we recursively split it as we move down the hierarchy. Let's look at an example of agglomerative clustering. First, we're going to start with a lot of examples, all taken from Star Wars. First thing we might do is find pairs of instances that are closest together. That might look like this, where the yellow means dark, the blue means light, and the two green are non-Jedi. As we continue to move from the bottom up, we might combine these two clusters into the Jedi cluster, and then we could group everyone, all 6 instances, into the all cluster. In contrast, a divisive hierarchical clustering algorithm would work like this. All the instances are in one cluster to begin with. Then we break out into 2 clusters, Jedi and non-Jedi. Next, we break out the Jedi cluster into the dark and light clusters. So what we've seen here is 2 ways of creating this hierarchy of clusters. So each cluster contains more clusters, which contains more clusters. We're going to consider in greater detail the agglomerative hierarchical clustering. We see the pseudocode on the left and a visualization of that on the right. First, we initialize m clusters, each containing one training instance. So every training instance is its own cluster. Next, we compute the distance from every cluster to every other cluster. So that looks something like this. But we have to do it between every cluster and every other cluster, which is a lot of comparisons. I'm just going to show 2 here. Next, based on those distance measures, we merge the 2 closest clusters. So whichever 2 clusters are closest get merged together. So in this example, it may be these 2 here. Now they're one cluster. We then repeat this process until all of the training examples are merged into a single cluster. Let me show you what that looks like. So we would next compute distances once again between a cluster and all the other clusters. And then based on that distance measure, choose the closest 2 and merge them. So perhaps it's this. We would continue doing this, computing all of the distances between all of the clusters and merging the closest 2, perhaps like so. As this is repeated, you'll see that the cluster begins to include more and more. As this process ends, all of the training examples will be in one cluster, as shown here. An important question to answer is, how do we compute distance? And we're going to compute distance the same way that we've been in this series. We're typically going to compute distance as the Euclidean distance, the ordinary distance in space between 2 points, using this distance formula here. Now that's half the problem, but we have another question as well, and that is, how do we compute the distance between clusters? That is, if we've got multiple data points in a cluster, how do we choose what point represents that cluster? This is also called linkage criteria in hierarchical clustering. The first option is we can choose the minimum distance between clusters. This is called single linkage clustering. In this case, the distance between 2 clusters is the distance between the 2 training examples that are closest to each other in those clusters. The problem here is called chaining. What that means is there can be a sequence of close observations in different groups that cause the groups to merge earlier than they really should have. Another option is to do the maximum intercluster distance. So in this case, we take the 2 points that are furthest away to compute cluster distance. This is called complete linkage clustering. The problem here is the opposite of the minimum, outliers. We may not merge two very close groups because there's an outlier that makes it appear as if those two clusters are far apart. The last option, which is maybe a happy middle, is the average. So if we take the average distance between two clusters and use that, it may be less sensitive to chaining and outliers. One issue here is, though, it is sensitive to the scale. So we can apply a slight transformation, even an equivalent transformation, and significantly change the results. So these are three ways of defining what's the distance between clusters. The output of hierarchical clustering is called a dendrogram, and this is what it looks like. Basically, we're seeing that there is this hierarchy where every hierarchy is split into two, and that tree basically keeps going down until there's one training example in each cluster. The nice thing about this visualization is it provides an interpretable way of viewing the algorithm and the data. It's up to the user to choose a natural clustering from this sequence. Here's another example that perhaps is more realistic to how a program would automatically plot this. The Dendrogram is a useful summarization tool, and it's part of why hierarchical clustering is popular, because this gives us an interesting hierarchical view of our data. Now, as we're concluding, I want to give you a word of warning. Hierarchical clustering should be treated with caution because different decisions about cluster group similarities can lead to vastly different cluster structures. Basically, this algorithm imposes a hierarchy on data, even if that hierarchy is not appropriate. It's going to find some hierarchy in any data because that's what we've told it to do. It is up to the user to interpret the results and choose a natural, appropriate clustering from this data. There's no real statistical foundation to this approach. Let's summarize hierarchical clustering. It's a simple algorithm that does produce a result that's interpretable and visualizable, and we can use that dendrogram as a summarization tool. On the downside, however, hierarchical clustering imposes this hierarchy on the data, even if it's not appropriate. It may be very sensitive to the linkage choice, that is the definition of intercluster distance. It's going to have significant computational overhead because we have to compute so many distances between all the points. And really, it has very little or no statistical basis. This has been a look at hierarchical clustering, which is an unsupervised method. I'm Keenan Casey for Tuts Plus. Thank you for watching.